Hi everyone. So today we are going to discuss on heap sort. It's a very important topic from an exam point of view, and I have seen many students skip this topic thinking it's difficult. But in fact, this is a simple topic. This video may take around say 30 to 40 minutes. Be with me, and I guarantee you that you are going to understand this one in a better way. Okay. So starting with heap sort, I'd like to call this different pieces of a puzzle. There are different portions or different topics in heap sort. One is that we must have prior knowledge. Then there is three algorithms. One is Max Heapify, another one is Heap, and another one is Heap Sort. So what we will do is we will study each pieces separately, and once we know each pieces, we will arrange them together in such a way that the entire picture is clear for you. So first we will be starting with the prior knowledge. Then we will move to Max Heapify. Once we are done with this, we will see how a build heap works. And once we know all these three, we can move to heap sort algorithm. Okay, so this will be the working pattern in which we will be studying. So once coming to prior knowledge, the requirements are you should be knowing how to represent a binary tree using an array. Or to put it in another way, suppose we are given an array, we should be able to create a binary tree. We will be seeing that. Then we will be seeing what is a max heap structure, and also we will see what is a min heap structure. Once we know all these things, we can move to Max Heapify. So we will start with prior knowledge. We will see it with an example. So consider we are having a binary tree 1, 2, 3, 4, 5. Suppose this is a binary tree and I have to represent it using an array. So to represent a binary tree in array, there are certain rules which you have to know. First one is that the root node will be in index position 1. So the array index starts from 1. So according to the first rule, your root node will be in index position 1. So your root node will be in index position 1. And next thing you have to know is the index of a left side will be 2 into I, where I is the index number of its parent. So suppose if I have to find the index position of 2, this node, the index of its parent is 1, and as it is the left side, it will be 2 into 1, which means it will be in index position 2. Similarly, for right side, it will be 2 into I plus 1, again where I is the index position of its parent node. So suppose if you want to find the index position of 3, node 3, we will first check the index of its parent, that is 1, then we will apply the formula, that is 2 into 1 plus 1, which means it will be 3. So 2 will be in index position 2 and 3 will be 3. Now suppose if we have to check the index position of 4, it is the right side. So formula is 2 into I plus 1, where I is the index position of its parent, that is 3. So it will be 2 into 3 plus 1, which means 4 will be in index position 7. What about 5? Again it is the right side. So 2 into I plus 1, where I is the index position of its parent, which is 2. So 2 into 4 plus 1, which means 5. So this will be the equivalent array representation of this binary tree. Now I will just give a question. Suppose if you are having a node say 20 over here, what will be the index position of 20? So this is the left side. So the formula is 2 into I, where I is the index position of its parent node, that is 2 into 7, which means 20 will be in index position 14. So there are certain advantages of using array, and similarly there are certain disadvantages of using array for tree representation or binary tree representation. I am not going into that. Suppose if we go, we will be deviating from the original topic. So I will say whatever is necessary. So these are the three rules you have to know for representing a binary tree in array. Fine. And we will do the reverse process also. Suppose if you are having an array, say 10, 20, 30, 40, 35, 70. I am considering an array like this, and I have to represent it as a binary tree. How we can do that? Root node will be in index position 1, which means 10 will be in the root position, and to the left of 10 you will be having 2 into 1, that is whatever is in index position 2, that is 20, and 30 will be 2 into 1 plus 1, that is index position 3. What about 40? Say 2 into 2, that is 4. 40 will be over here, and suppose if you write again, this will be the tree you are getting. So if we are having an array, you can simply write it in level order, and you will get the equivalent binary tree. Okay. So whenever you are representing an array as a binary tree, you will be getting a partially complete binary tree. There will not be any vacant positions in between the array. I hope it is clear for you. So this is how you can construct or visualize an array as a binary tree. I hope it is clear for you. Now we'll see what is max heap and what is min heap. Again we will do it with an example. So considering max heap 50, 40, 50, 20. Okay. 1, 2, 3, 4, 5, 6. These are the index positions and these are the values. So this is an example of max heap. Whenever we are saying a heap structure, keep in mind that it will be a partially complete or a complete binary tree. So from example you can see that here you are having a value 50, child nodes are 40 and 30, and again for 40 you are having two childs with value 20 and 25, and for 30 you are having two child values with 27 and 24. So the max heap defines, or it is defined as, all the internal nodes of a binary tree will be having values which is greater than its child nodes. Every internal node will be having a value which is greater than its child nodes. So suppose if we take 50, you can see that the value is greater than its child nodes, 40 and 30. 50 is greater than 40 and 50 is greater than 30. Similarly, 40 is an internal node. If you check that, you can see the child nodes are having value 20 and 25, and 40 is greater than that. So for all the internal nodes, if this property satisfies, we can say that it is a max heap. So this is a max heap. Similarly, if you see min heap, every internal node will be having a value which is less than its child nodes. So you can see every internal node is having a value which is less than its child nodes. That is called as a min heap. So interestingly, you can see that the largest node in a max heap will be its root node, and similarly in a min heap the smallest element will be its root node. So this much information you need before going to actual heap sort. I hope this much thing is clear for you. The array representation, or once an array is given, I hope you can convert it into a binary or complete binary tree or a partially complete binary tree. And now you know what is a max heap structure and what's the min heap structure. So it will be a partially complete or complete binary tree with an additional property. Suppose if it is a max heap, all the internal nodes will be having value greater than its child nodes, and if it is a min heap, all the internal nodes will be having a value which is less than its child nodes. I hope it is clear for you. Now we will move to Max Heapify algorithm. So this is the most important part of Heap Sort. So now we will see the working of Max Heapify. As I have mentioned earlier, this is the most important topic in Heap Sort. Once you are clear with Max Heapify, the entire thing will be simple for you. Okay. So you will be watching this on your mobile or laptop probably. I have a request. Please keep your entire focus on this topic. If you are doing some other work, if you are multitasking, please stop it for a while. If you need, you can take a break and you can come back. We need the complete attention for this topic. Okay. So let's start. So we are considering an example for Max Heapify. So now we are having a binary tree and we are considering a sub part of it. Okay. So here first we are going to call Max Heapify of 6. I'll say why we are going with 6. Suppose if you are taking this subtree, you can see that the left subtree of 20, this node, the left subtree of 20 is already satisfying the max heap property. You can see 50 is greater than 30 and 25, 30 is greater than 10. So the left subtree is already a max heap. Similarly, if you see the right subtree of 20, that is also satisfying the max heap property. But when we include 20 into it, the entire thing is not a max heap. So what Max Heapify does is that if you call a Max Heapify at a certain index, and suppose if its left subtree and right subtree is already satisfying max heap, this function call will convert this entire sub portion into a max heap. So that's what it does. We'll see it with the example, see the working. So now this is index I, that is 6. Here we have called Max Heapify. Once you know this index, we can find the index of its left child. We will all use the formula 2 into I, that is 12. In 12th index, you will be having the left child, and 2 into 6 plus 1, that is in 13th index, we will be having the right child. So now we will find the largest among these three nodes. So 20, 50 and 40. So 50 is the largest. So what we are going to do? We will interchange 50 and 20. So that the largest node will be over here. Now as here we have made a change over here, there is a possibility that the max heap property may have been violated. So once if there is an interchange, we will again call Max Heapify at that position. So there will be a Max Heapify call at 12. So again we will find the left child of index position 12, that is 20, and we will find the right child. We will find the largest among three, 20, 30 and 25. So this is the largest. We will interchange it. So 30 will come over here, 20 will be over here. Again, as there was a change, again there will be a Max Heapify call. So there will be a Max Heapify call at index position 24. Now again we have to check with this left child and right child. The left child will be in index position 48. So we have got that. And the right child will be in index position 49. That is 2 into 24 plus 1. But you can see that there is no right child for this node. So here the heap size itself is 48. So that is the length of array. And we have got the right child, position of right child as 49, which is greater than the heap size, which means there is no such node. So there is no need to compare with right child. We will just compare this node with left child. Already 20 is larger, so there is no need to swap. So this is the time when we stop the function called Max Heapify. And now if you see the tree, you can see that the entire thing has become a max heap. So we will see the three different cases. So when we call it Max Heapify at this position, here the heap size is 3. We are having only 3 nodes. So first when we check with 70, 90 and 80, the left child is having the largest value. Suppose if the left child is having largest value, we will interchange the value of left child with root node. That means the tree will become 90, 70 and 80. So that is the case 1, left child with largest node. We will swap. After swapping, we will be having a function call again. There will be a max Heapify at position 2. But as you can see, there is no left hand child, right child for 2 because heap size is only 3. Left child is at position 4 and right child is at position 5. So there will not be any further function call. This will be a final max heap. And this is case 2. Again, you are checking with the largest. Here, right child is the largest. So 90 will be interchanged with 70. Again, we will check for the left and right child. In this case, we are not having that, so we will stop the process. And third case is that we are having a left subtree which is already satisfying max heap property. We are having a right subtree which is already satisfying max heap property. And when we check, already the largest node is the root, which means there will not be any swap. This is already in max heap structure. Okay, I think the working is clear for you, but still we will see one more example. Just for the sake of doing, we will see one more example. Okay, we will see a tree, say 50, 40, 30, 20, 60, 45, 35 and say 25. So you can see this is already a max heap. This is also already a max heap, and here is the place where we are having a violation. So here we will call max Heapify of child called as 1, 2, 3, 4, 5, 6, 7, 8. So the heap size is 8. We are calling max Heapify of 1. First we will find the largest among the 3, which is 60. So 60 will be interchanged with 25. So again we will find the left child of 25 and right child of 25. We will find the largest among the 3, that is 45. So 45 will come over here. 25 will come over here. Again there is a change, which means there will be a max Heapify call over here. There is no left and right child. So this is the place where we will be stopping the process, and you can see we are having a max heap. Okay. So I think the working of max Heapify is clear for you. Now we will go into the algorithm for max Heapify. So from here itself, I think you must have got some idea. So what we are going to do, we are giving or passing a index value. We are going to find the left and right child of that particular index position and check whether that is a valid or not. If it is valid, we will find the largest among 3 and it will be swapped with the largest position. And if there is a swap to that new position, we are again calling the same function max Heapify, which means there will be a recursion. Okay. And what will be the stopping condition? Case 3. If it is already the largest node, there is no need to swap. If there is no left or right child, again there will not be any swap. Okay. We will see it with the algorithm. Okay. Okay. Now we will see the algorithm of max Heapify. It's a very small algorithm. You can see there is a recursive call. We will see how it works. So first we will be passing the array along with the index to be called. So considering this example, we will be first calling max Heapify a comma 2. There is a first call max Heapify a comma 2. So this will be the index we are interested in. Okay. So what we have to do, we have to check it with the child nodes. So first we have to find the left index. So L is equal to 2 into I. So in this case, L will be, the left child will be in index position 4 and right child will be in index position 5. So first we are finding the index of left and right, and here you can see the heap size is 11, which is the length of array. And now first we are checking whether it is a valid node. If it is a valid node, left child will be, or the index of left child will be less than heap size. So 4 is less than 11, which means it is a valid node. And next we are checking whether A of L is less than A of I. We are checking whether 50 is greater than 20. So 50 is greater than 20. So we are making a modification. We are setting largest as left. So we are introducing a new variable which is largest. So we have checked these two nodes, and between these two nodes, largest is index position 4. So we have updated that. Suppose if this condition is false, then we are setting largest as I itself. So when will be that case? Say suppose we are having 30, 20, 50. This will be index position I. This will be L. You can see AFL is not greater than AFI. In that case, largest will be set as I. This means largest will be pointing to this location. Okay. Now we have to check with the right child. So what we are doing? We are checking whether R is a valid node. So R is less than or equal to heap size. Here you can see that it is a valid node. And we are checking whether A of R is greater than A of largest. Which means I am checking whether 60 is greater than, now largest is index position 4. So I am checking whether 60 is larger than 50. It is. So what we will do? Then we will modify largest as right position. So now the position of largest is 5. Okay. Now we are checking whether largest is not equal to I. Why we are checking that? We have to know whether there is a swapping required or not. If largest is not equal to I, the meaning is that it is either left child or right child, which means there is a need of swapping. So if largest is not equal to I, we are going to swap AFI with AF largest. So in this example, we will be swapping 20 and 60. So 60 will be coming over here and 20 will be coming over here. And what will be the next call? Again we are calling Max Heapify A, largest. So there is another recursive call from here, that is Max Heapify A, largest is 5. So it will be A, 5. Okay. Again we are going to the same function. We are going to find left and right. So left will be this time. Left will be A into 2 into I, that is 2 into 5. Left will be 10. Right will be 11. So we have found these two. We are checking whether large is a valid node or not. 10 less than or equal to 11. So it is a valid node. We are checking whether AFL is greater than AFI. That is 40 is greater than 20. It is true. So largest will be having position 10 now. Next we are checking whether R is a valid node. Yes, 11 less than or equal to heap size. So it is a valid node. Whether AFR is greater than AF largest. Whether 30 is greater than 40. No, the condition is false. So largest will remain as 10 itself. Again we are checking whether largest is equal to I. Whether 10 is equal to 5. No, condition is false. So which means there is another swap required. So largest and I will be swapped. So 40 will come over here and 20 will be over here. Okay, so this much is clear. Now again there will be a Max Heapify call, that is Max Heapify A, 10. We will do the same process again. Now left child will be in position 20 and right child will be in position 21. Because 2 into 10 and 2 into 10 plus 1. We are going to check if L is a valid node. Position 20 is greater than heap size, which means it is not a valid node. So condition becomes false. It will come to L spot and largest will be set as I. So largest will be again 10 itself. Now again we are checking if R is less than or equal to heap size. Again condition is false. It is not a valid node. So it will come to line number 5. I am checking whether largest not equal to I. Largest is 10. I is also 10. Which means this condition is also false. We will come to line number 6 and here we will return from the function. So it will go to return. It will go back. Okay. So this will be the final reposition, and if you are writing the array, it will be 60, 50, 40, 25, 35, 10 and 30. So that is how a Max Heapify works. I think the algorithm is also clear for you. So I'll just recap. So this much portion is finding the left and right child. Now we are checking. So this much is to check the largest among three nodes. The root node, its left child and its right child. We are also checking whether it is a valid node or not. If it is valid, we are checking the largest. And we are introduced a new variable which will be holding the index position of largest node. And if it is not equal to I, what we will do? There will be a swap and there will be a recursive function call. I hope it is clear for you. So far we have seen how Max Heapify works, and we have also seen some prior knowledge about how to represent a tree using array. So next we are going to see build heap. So I'm sure you are curious on we haven't started yet with the heap sorting, but let me tell you, we will be getting into that. But before that, as I have said earlier, we have to see each individual pieces first. Once we are clear with that, it will be so simple that we can rearrange them and we can understand how heap sort works. So our next aim is to understand build heap, which means suppose if we are given an array, this will be the virtual tree structure of that array. Now we have to convert that into a max heap. That is our target. For that, we will be using the property of Max Heapify. Okay, we can see. Now forget about the algorithm. Don't look at it. We'll come to it. So we are having an array A with 6 elements. That is heap size is 6 with 50, 10, 30, 20, 40 and 60 as elements. I have represented it as a binary tree, a partially complete binary tree. So now my aim is to convert this into a max heap. Okay. So we will see how we can do that. So we are having a tree. I have marked the index positions. This is a leaf node. This is a leaf node. This is a leaf node. So we are not worried about the leaf nodes because the Max Heapify defines that all the internal nodes should be having a value which is greater than the child nodes. So as far as leaf nodes are considered, it can be treated as a max heap. So suppose if we check 30 at index position 3, here you can see the left subtree is already a max heap and right subtree, there is no such right subtree. So now suppose if we can call Max Heapify at 3, we can convert this much into a max heap. Is it right? So first, suppose if I call Max Heapify of 3. So 60 we are not considered because it is a leaf node. This is a leaf node. This is a leaf node. Once we come to 30, it is not a leaf node. It is an internal node. So we have to consider it. So I called Max Heapify of 3. It is having a left subtree which is already a max heap. So next we will check as for according to the Max Heapify property, 60 will come over here, 30 will come over here. There will be again a recursive call at 30 which will not make any difference. So now this much has converted into a max heap. So next what we have to call? Next we will be calling Max Heapify of 2 because this is also an internal node with left subtree as a max heap and right subtree as a max heap because these are leaf nodes. So once we call Max Heapify of 2, again largest will be 40. So 40 will come over here and 10 will come over here. Again there will be a recursive call which will not make any difference. So now this much is converted into a max heap. Now second one, when we call Max Heapify of 1, you can see that the left subtree is already a max heap and right subtree is also a max heap, which means you can call Max Heapify. So largest is 60, so 60 will come over here, 50 will be over here. Next there will be a Max Heapify call at 3, 50 and 30 will be compared. 50 is the largest, so it will remain as is. Now we can see that the tree is 60, 40, 50, 20, 10, 30 which is a max heap and array will be changed as 60, 40, 50, 20, 10 and 30. You can see that you are having a max heap structure. So given an array, what you can do, you can call Heapify multiple times and you can convert it into a max heap. So what was the procedure? We can discard all the leaf nodes and we will start from the first internal node, that is the internal node with largest index position, that is Max Heapify. In this case it was 3, Max Heapify of 3. Then we will call Max Heapify of 2 and we will do this process until we reach the root node. So that will be the procedure. So first thing, we have to find out the index position of this node, that is the first parent or the parent with largest index. For that, what we will be doing is that we will find the last node, that is the length of array, that is in this case length of array is 6. So first thing, we have to find the parent of that node. How can we find the parent? It is nothing but I by 2, where I is the index of child node. So we will find the last child node and we will divide it by 2 so that we will get the index of its parent position. Suppose if we were having another node, say 5 at index position 7, again we will be doing 7 by 2, which is 3. So again the parent will be this position. Now we will see the algorithm as well, how to convert a build heap. First thing is that we are setting heap size as length of A. In this example it will be 6 or 7. Now for I is equal to length of A by 2, which means we are starting at the first parent, okay, and then we will move up to 1, which means we will decrement by 1 until we reach 1, and we will call Max Heapify A of I. So first time in this example it will be first time Max Heapify of 3, then it will be Max Heapify of 2, then it will be Max Heapify of 1. Suppose if we are having a larger tree, say suppose I am having 15, 30. Suppose if I am having 9 nodes in my array, if I am having 9 nodes, heap size will be 9. The first parent will be 9 by 2, that is 4. So first I will be calling Max Heapify of 4, which means this much portion will be converted to a max heap. Then I will call Max Heapify of 3. So this much will be converted to a max heap. Then when I call Max Heapify of 2, you can see that this is already a max heap. Right subtree is also already a max heap. So this much can be converted into a max heap. And then on Max Heapify of 1, you will turn the entire tree into a max heap. So this is how we can convert a given array into a max heap. And why we are doing that? There's one more property for max heap. Once a tree is constructed as a max heap, you know that the largest node will be in position root or in index position 1. So we will be making use of that property to sort the array. So we will be having the largest node in index position 1. So you can simply swap it with the last location so that you can arrange the array into ascending order. That's what we are going to do in the next algorithm, that is heap sort algorithm. So finally we have reached the final stage, heap sort. So in the last stage we have seen an array was given and we have converted it into a max heap. So that is where we are going to start now. So from here what we are going to do is, using a max heap we can arrange the array in ascending order. So what we will be making use of, you can see that the largest element is at the root position. So in an ascending order that should be at the last location. So what you can do, you can swap 60 with the last position. So 30 will be over here and 60 will be over here. So in array the position will be like this, position will be 60 and 30 will be interchanged, and now you can see that 60, this position has get sorted, which means we do not have to do anything on index position 6 further. So for that what we will be doing is that we will be reducing heap size by 1. That is, in our virtual tree we are not going to consider this node again because this is already sorted. So we are just considering these 5 nodes now. Now you can see that again the max heap property has been violated. This is not a max heap anymore because we have swapped the last node to root position, which means there is a violation. Now again how we can convert it back to a max heap? Do we not need to call build heap? No, actually not. Now we can see that there's already a max heap structure. The only difference we made was that we removed the last node and that value has been put into root node. So you can see this part is unaffected, which means already this is a max heap. So the left subtree is already a max heap and right subtree is also a max heap. So instead of calling build heap, you can simply call max heapify of a comma 1, which is the root position. If you call max heapify of 1, again this entire tree will become a max heap. So we will be calling max heapify of 1. So largest is 50. 50 will come over here and 30 will come over here. So in your array it will be 30 and 50. So we have again converted the tree into a max heap. Now what we know, the second largest element is at your root position. So 50 can be swapped with position 5 or the last node is swapped with 50 with your root node. Now what you know that the second node is also sorted, which means in your virtual tree this is no more needed, which means heap size will be again reduced by 1. Now again we are having the tree which is not a max heap. So again what we will do, we will again call max heapify of 1, which means again on this tree we will do a max heapify of 1, which means 40 will be over here, 10 will come over here, again there will be a recursive call, so 20 will be coming over here, 10 will be over here. So the array will be 40, 20, 30, 10. Again we are going to do a swap with 40 and 4. So 10 will be over here and 40 will be over here. So third node will also get sorted. So 40 will be over here, 10 will be over here. Heap size will be reduced by 1. So we are not considering 40 anymore. This will be our current tree. Again we will call max heapify of 1, which means 30 will be over here, 10 will be over here. That is 30 over 1 and 10 will be here. Again we will do a swap. So 30 will come over here, 10 will be over here. So 10 will be here. We will discard this node. Again we will call a max heapify on 10. So 10, 20 will be over, 10 will be over here, 20 over here, 10 over here. Again we need a swap. So 20 will be coming over here, 10 will be over here. This much is sorted, which means there is our array is already sorted. Just like in bubble sort or something, if you are having n elements, you require only n minus 1 passes. Similarly, here also, if there are n elements, we will be requiring only n minus 1 swaps. At that point, when we swap 20 and 10, the entire array will get sorted. Okay. So this is how your heap sort is going to work. We will see with another example. Before that, we will have a look at the algorithm. Okay. So algorithm for heap sort. First thing, we are having a random array. First thing, we have to convert it into a max heap. For that, what we will call? We will call the function build heap. So that after this function call, the array will be converted to a max heap. Now, you are having n minus 1 passes. So from the last location, that is length of it. So in this example, it will be 6. So initial value of I will be 6 and it will move up to 2, which means from the last position until 2, that is 1, 2, 3, 4, 5. We are having 6 elements, we will be having 5 passes. That is n minus 1. So initial value of I will be 6. And what you are doing? You are swapping it with the first location. As it is a max heap, first location will be having the largest value. So first time 60 will be coming to the last position, which means last position is get sorted. Once that is sorted, we are reducing heap size by 1 because from our tree structure we are discarding 60. Okay. Then what you have to, now you are having 5 elements in consideration, and as you have swapped it with the last position, your first root node, including root node, it is not a max heap anymore. So to convert it into max heap, what you will call? You will call max heapify of A of 1. I'll just draw another max heap. Suppose this is the case. See, 50, 30, 20, 10. Suppose this was the max heap. Initially, I value will be equal to 5. Then we are going to swap A of 1 and A of I. That is 10 will come over here and 60 will be over here. So in your array, the fifth index will be 60. The largest element has get sorted. So that is this line. Then heap size is reduced to 1, which means from the tree structure, you are discarding this part. Now this is no more a max heap because the initial node, the root node is having a value 10, which is not greater than its child nodes. But still, this part is a max heap and this is a max heap. So to convert it back to a max heap structure, what we will call max heapify A of 1. So what will happen? 50 will come over here, 10 will come over here. Again, there will be a recursive call. 20 will come over here and 10 will be over here. So that will then again it will move. I value will be decremented. So from 5, now I value will become 4. We are swapping A of 4 and A of 1. So 50 will come over here, 10 will come over here. So second element is also got sorted. After sorting the second element, we are discarding this element, that is heap size will be reduced by 1. Now we have to convert this back into a max heap. So we will call max heapify of 1. So 30 will be over here, 10 will be over here. Again, I will be decremented from 4, I value will become 3. Again, we are going to swap A of 1 and A of 5, that is 30 and 10. So 30 will come to the third index of the array. Now that is also sorted. As it is sorted, we are discarding it from our tree structure. Again, we will call a max heapify of A of 1, which means this will be converted back to a max heap. Again, I value will be decremented to 2. We are swapping 20 and 10. So 10 will be over here, 20 will be over here. Now there is no need to, again there will be max heapify call, but now the I value has become 2 and we will stop the process and we are having the array in sorted order. Similarly, you can do sorting in descending order where we will be using a min heap instead of a max heap. Okay, the entire thing is clear for you now. Thank you.